All right, then. Um, so if you look at the lecture notes that I posted on Vuex, you see that there is some stuff that I didn't get to cover in the last lecture. So let's just start with that. Okay, so the idea is we want to talk about reversible systems and quasi or quasi or quasi uh, static processes. Okay. Um, okay. So so if I change the system very, very rapidly, so for example, we can take like a gas, an ideal gas for as an example, and I change the pressure. I change the volume suddenly. I either compress it or I expand the volume. Okay, Abdullah Rafi Mahmoud, can you make sure that you accept the uh, invitation to the class on my Google Calendar, so that when you come, I won't have to allow you in. You can just automatically, you can just enter the class. Okay. Okay. So, so systems where we change the one of the parameters very suddenly, then what happens is that then it pushes our system away from equilibrium. When it pushes our system away from the equilibrium, we don't know where the system is until it settles into an equilibrium. So what we are interested in thermodynamics is that we are interested in quasi-static or quasi-static changes. So what it means that, so if you have a system, suppose a gas, and a gas is parameterized by two state variables, say pressure and volume, and suppose we know what both the pressure and the volume is. So then, what we do is that we change the pressure or the volume in such a way that it's almost infinitesimal. So we change the pressure a little bit and the volume a little bit, so that whatever trajectory the system takes, every point on the trajectory, its parameters are well defined. So such a process is called quasi-static. And what it means is that you are changing everything infinitesimally. Suppose you change the pressure just a tiny bit so that your volume changes a tiny bit. So if you zoom in, you're just changing a little bit, and you're almost going away from the equilibrium between these 2 points. Okay, but you're not going away too far. So the limit is, of course, this becomes infinitesimally small, and then to get from, say, this point A to this point B, you need to do an infinite number of these things. Of course, no one has infinite time, and human processes, you can't really do infinite number of steps. So this is an idealization to something that we do in lab. So in the lab, you do it slowly, but of course, and what we discuss here is kind of the approximation to that, and that's called a quasi-static process. And because in a quasi-static process, as long as we are not doing anything drastic to the system, such as the system is not going through some, phase transition, or say some chemical changes, for example, irreversible chemical changes, because we know the path to the state space, if we go this way, we can always go the opposite way. So such processes are called reversible processes. Okay. Now, before we go on to do some physics, let me just, I think, discuss the state variable that we introduced in the first law, the state function. The first law essentially says that there exists a state function called, which we are calling energy. And for the gas, the state function is a function of P and V. Now, from a mathematical point of view, if you change the underlying variable slightly, then it induces a little change in your state function. And that little change is going to be given by using the chain rule is given by this, right? So this is from multivariate calculus, multivariable calculus, and right. So you can be redundant, and you can say that this first term we are taking the derivative of E with respect to P, but keeping V constant. And in the second term, we are taking the derivative of E with respect to V, but keeping the pressure constant, okay? So this is the function. So this is an exact differential. And this is basically, this is expressing how, when you change the underlying pressure and the volume, how the function changes mathematically. But under a quasi or a quasi-static process, the change in the infinitesimal change in your energy is due to the work that you're doing on the system, which is not a state, it is not a state variable, and the energy or the heat energy that is absorbed by the system, right? So, these are not exact differential. That's why we use this, we use this notation, D, there's a bar, W. So what does this mean mathematically? Mathematically means that, there doesn't, so there is, so for example, there is no function such that its differential is given by this, okay? And what do I mean by that? So let me just look at it more specifically. So if you have, say, a gas, in some container, so it's a gas in some container, and suppose it's got adiabatic walls, so that no heat can escape, and so this is the gas inside. So and then what you do is that you have a piston, and using that piston you can do some work on the gas, right? So if you press the piston, suppose the piston moves a little bit, and this is, say, d of x, then, but you apply force F, right? So what is the force what work that you did on the, on this guy? The work that you did on this guy is going to be F times the displacement, right? But there's a cross-sectional area for this piston, and that cross-sectional area is A. And so we can divide F by that cross-sectional area and multiply d of x by A. But what is the first thing? The first thing is nothing but the pressure that is being applied on the gas by this piston. And if we are in a quasi-static process, then of course this pressure is the same as the pressure on the gas, because they're always in equilibrium approximately. And this thing is going to be the change in the volume. So we see that the work that we do is equal to P times dV. So this is what I'm trying to was saying is that d of W has this P dV, means that there is no function f, say a function of P and V, such that when you take its differential, that it becomes P of dV, right? Because you know, you can show this. Otherwise, there'll be another term by Leibniz, right? So that means that this thing, because this thing cannot. Okay, somebody's here. All right. So Tonmoy, can you make sure that you accept the invitation to the Google Calendar so that next time you come to class, I won't have to like let you in. So, all right. So let's get back to this. So what I was saying is that,
Sir, I have a question.
yes.
So the dW, so you're saying it's not an exact differential. So I was thinking about work done by conservative fields.
Yeah.
Uh, so won't that create exact differentials? I was wondering.
Work done by conservative field. So you're saying, say, in electromagnetism.
Or just gravity simply. Yeah.
Gravity is what would be the, if you just let, it's going to be work done by conservative fields. So work done by conservative fields,
I was wondering whether exact differentials kind of do correspond to conservative fields, don't they, sir? I don't know. I mean,
yeah. I mean,
uh,
basically, what the thing that we said was that the state functions correspond to exact differential. If we take a state function and the value of the state function doesn't depend on the path, right? And that's exactly the definition of a conservative field, is that something
yeah,
where the work you
yes,
do does not depend on the path. So yeah, I would agree there.
yes.
Yeah. All right. So
Also,
that's,
in general, we're just assuming it to be inexact.
but here we are not using conservative fields. I mean, we are doing work using pressure and volume.
Oh, okay.
This is what I'm saying is that this guy, this is not an exact differential because there is no function such that when you take its exterior derivative, you get this.
I see, sir.
Okay, so that's why we are using, this bar sort of, and it is just to kind of make sure that we can differentiate, because when we do work by these processes, the energy also changes by a small amount, which we use dE. But this here, it's also the energy is changing by a small amount when we change the pressure of the volume. But here, this is an exact differential, whereas this is made out of differential which are not exact. Okay.
Okay, sir.
Okay. All right. So we see that. Okay. Now that work can be written as, for the gas case, PdV. Now let's look at some sign convention. So if the if heat is absorbed by the system, that is d of q. Okay, Afia, I will put you down as present. Who else came later?
Sir, me.
Sir, I was a little late.
Who's
Me as well.
I? Please tell me your name because I cannot see your face. So
Mehdat.
Sir,
okay,
Sir Nahi.
Nahi, Mehdat. Who was the other?
Shitima, sorry.
Okay.
Abdullah Rafi Mahmood.
Abdullah ke kursi. Sitima is okay. Sitima is present, and Mehdat is present.
Sir Savin.
Savin, okay, is present. Anyone else? Nusaiba, Zabir, Rahul, Wajiha, Mahfuz. Farhan, are you here? You're here. I saw you. Farhan, Rafid, Sheikh Farhan Rafid. Okay, I thought I saw you. Yes, sir. Okay, you're having voice problems. Okay, you are present. Oishik? No Oishik. Okay. All right. So let me go back to my physics then. Right. So when the system absorbs heat, we say D of Q is positive. And when the system, it does work, then so when the system does work, it should like lose some energy, right? So that then, we say D of W is a negative, so we get minus P of dV. So in general, we say dE is dQ minus P dV, okay? Here we are using this as a gas, for the gas. Okay. All right, any questions? Okay, let me carry on with the discussion of, quasi-static and reversible processes. So in thermodynamics, we are interested in reversible processes. This means that we can track such a system through the state space, and such processes are quasi-static. So if these processes weren't, then they would deviate violently from equilibrium, and then we would not know where their position would be on the state space, and we wouldn't be able to, call them reversible, right? So for the gas, we can have, let's look at some example. So for the gas, the state space is V and P. We can also express the state space in terms of T and V and other. We can replace T for one of these things, because using the equation of state, we can, eliminate one of the. We can exchange one of the state variable for another state variable. Okay. So we can start, say, here, which is P1, V1. We can end up here, P2, V2. And we can go use one path to get here, and then we can use another path to get back. So after such a cycle, what is the change in the energy? What is this? Can somebody tell me?
It's the area enclosed by the loop.
Okay. So what is it?
Sir, exactly what do you mean? What is it? I mean, the enclosed area. So,
okay, yeah. Anybody else wants to go?
Heat?
Okay.
So can it be said that extra energy that was lost in the process of changing the state?
Right. So what is E? E is what kind of variable is this?
State variable.
So what did we prove about state variables? Or what did we say about state variables, which I said was almost trivial, but
I see. Energy should not change in a complete cycle.
so the value of the state variable only depends on its endpoints, right? Right?
Yeah.
Yes.
So if I change the system, I take it over like a cyclic process, what should be the change in the state variable, state function? What should this be? Nahi?
Yes, sir.
What is it?
Oh, okay. So it should be 0, I presume, since it's a state variable.
Very good. Right. So, I mean, you can see that, if you just look at the first part of the process, say 1, then of course the area under the curve, right? That would be the work done, right? And that would be given by some integral of, PdV, right? So that would be some, but that's not what we are looking for. We are looking for and then if you come back, then we would have to subtract this part, and that would be, so the network would be the work that is enclosed in the, but that's not what we're looking for. We are looking for the change in the total energy. All right. So that means that the total heat that was absorbed during this cycle, which is Q, and which is given by, say, the integral of dq, has to be equal to the total amount of work done. Okay. Now, here, we can see that, the work that, this guy does is, is it positive or negative?
Positive.
Right. So therefore, it has absorbed energy, right? So if it went the other way, then it would do, because it's an integral, right? So, it has an orientation. If the process went in the opposite direction, it would be negative work, and therefore it would give up heat. Is that clear?
Because you would be subtracting a larger area from a smaller area.
Yeah, exactly. Yeah. All right, cool. Who was that, by the way?
Sorry.
Okay, good save. So the orientation in which you do the work determines whether you are absorbing heat or giving up heat. Okay, so this is an important observation. Now, why are we interested in reversible processes? Many of our real life, realistic engines are not reversible. I mean, they are reversible, but they're not quasi-static, right? So for example, a car engine, right, it's reversible, but it's not quasi-static. There are explosions happening but we are used to, so here, we are talking about quasi-static because, we want to, track our system moment by moment, right? But we want reversibility to be a useful feature of engines in general, because that's how you can, suppose I give you a lot of wood, a lot of things to burn, and then, or a lot of oil, or a lot of electricity or something, then you want the ideal thing, an ideal engine is something that just churns out work. So for it to be able to churn out work, indefinitely, it should be a reversible engine, right? So that's why we are interested in reversible systems. So let's just write down some words. Although I will give you lecture notes. Reversible systems are useful because we can use them to transform heat into work continuously or indefinitely.